Hello, everybody. I hope everybody likes the conference. I see people are relatively far to the back. I'm going to do some live coding, and the font is probably not super big, so you may not see very well. You may want to come closer to the front. What I want to talk about is, I refer to structured networking, referencing the idea of structured concurrency, which itself, again, is the idea of you basically, when you do asynchronous operation or concurrent operations, it would be nice if you could basically do the same thing which helped us out in, with the actual code writing, getting structured, do the same with concurrency. And there's a proposal, P2300, which kind of does that for concurrency in general, mostly targeting algorithms operating on GPUs and multiple threads. And I'm personally not that much interested in that area. I'm more interested in networking. And my main interest is to make sure that networking can integrate with what they do over there. And I want to show how that can be implemented, how that could look like. So, and I will jump right in. So my objective is to provide a basis for networking. There is, of course, ASIO. ASIO does not quite do the same things. I think the structured networking can be implemented on top of ASIO or vice versa. I have no stake in whether ASIO should get standardized as is. What I do want to do, however, is if structured networking, as in P2300, the sender-receiver stuff, if that gets standardized, that it integrates well with networking. And this is what I'm talking about. What I present is entirely experimental. There's no official proposal. And I will actually do a simplified version which doesn't do all the things. So what is the idea? As usual, you want to decompose your operations. And you decompose into basically senders representing work. And you have algorithm combining them. And eventually, when a sender completes work, it sends results basically by invoking functions on a receiver. So the sender-receiver has nothing to do with the networking, sending something over the networking and receiving something over the networking. It's the concurrency abstraction. And the idea is you take senders, receivers, put them together, you get an entity which you can start, and then everything should happen. So I get a little bit more detail on that on a very, very high level. And I start off with something which the user code typically doesn't really see, and that is the receiver. The receiver is basically the place where operations get completed. There are some things which you can query about the receiver. This is the left side, this getEnv. We get some kind of context, and from the context you can get something like a stop code token and an allocator and maybe a scheduler, whatever is needed for the corresponding algorithm. And the right side is basically the completion signals. The idea is a sender will, once the operation gets started, will always send one of the completion signals to indicate that things are done. And the completion signals are basically set value for a somehow successful result, set error for essentially an exceptional branch. There's no good result. It's kind of an error. And set stopped. This is the unusual thing which we normally don't have in normal programming. This is a cancellation channel. So if the operation actually got canceled, something told the thing via a stop token injected to say, all right, please stop. We don't need the result. It will just call set stopped and say, all right, I don't have anything to say. And that gets combined with a sender. Sender, this is basically a few slides representing different kinds of senders. One is a factory thingy, for example, starting a schedule. The senders I will implement today are mostly of that kind. There will be factories for doing network operations. And then adapters, it could be something like a then, or way more interesting like then is something like a when all. They can have multiple senders and they can all be started concurrently, and when all completes, when all of them are finished. And if one of them errors out, it can cancel the others to say, right, okay, there's one error, we will go with that error, and the other things we don't need, things like that. And then there's also kind of a consuming thing to say, right, we have algorithms to say, right, we consume the result of senders, and this is kind of an endpoint. And taking the key operation on a sender is connect, which takes a sender and a receiver. And the sender sends the result to the receiver, and it produces an operation state. The operation state is the entity holding the things all together. And the only operation on the operation state is start. Right? It's produced by connect, and you can do a start of it. What is interesting is the operation state is not movable or copyable. So this entire thing relies on a guaranteed copy elision. So when you call connect, you get something back which you need to put directly into the place where you want it. But it's possible to put it into a member or into calling new with that entity, so you can put it in whatever location you need to, but it's itself not movable. So these are the key operations. Basically, we get a sender with its set value, set error, set stopped, a sender with connect, producing an operation state, and then start to run it. And this is, roughly speaking, the entire core. For the implementation today, I will entirely ignore cancellation. It could be done, but I don't think I can fit that into the time to actually code that up. And then just to represent a little bit more complicated situation, like first something like a sender is built up, in this case when all with a then or two thens in there, which in turn have different things inside. And then the connect turns that into an entity, which is all in one memory location. There's no allocation happening over here. There's no, it's all kind of one structure. And so I put these circles into the squares to indicate that things are injected into the level up. You don't have that on the sender, so it's basically kind of a two-phase construction of things. First the sender building things up, and then the connect injecting these things into things down. So this is the high-level idea. Lucian yesterday or on Wednesday talked a little bit more about these things from a more abstract level. I want to go full on concrete. So coding time. I want to actually create a basic take an existing sequential echo server. Echo server is basically a request response thingy, where the response is just a trivial conversion. So I don't want to care about that. I take a sequential echo server and turn that into a fully asynchronous thing. That's the plan. Coding time, I'm not done yet, so I want to switch to coding. So there's a little bit of an environment I need because, well, so there's a whole bunch of headers which I may use. Then there's a very simple class. The state, I said, is not movable. So I have an immovable base class to basically make sure the thing indeed does not move. It's basically just a default constructor and a deleted move constructor, removing all the other constructors. And then there's a bigger thingy. There were a number of coroutine talks. This task thingy over here is a coroutine. It's completely implemented over here. There's nothing magical from outside other than standard library things. But it's too long to actually talk through that. I think I would spend an hour to just explain the task. The idea of that task is when you co-weight an entity, it expects that the entity is a sender. And you can co-weight multiple places, obviously, every time it's a sender. It just turns that into an awaitable, awaits that thing, and carries on. And the task itself is also a sender. So you can basically use a coroutine to build senders out of existing senders. This is what this task is. There's nothing complicated in here, really. It's basically just you go through the coroutine stuff and fill in the things, and that's it. Okay, and then I have another small class. It's just a resource manager for a file descriptor. Super simple. You can take a file descriptor, you can move it, destroy it, that's it. And then here's a network program. I guess everybody, or most people understand how networking works. At least this is kind of the Unix way, the Windows way using the Windows sockets is very similar. It uses slightly different names for the types, but mostly it's just the same. So the idea is we start off, create a socket, bind the socket to an address, listen on it, and basically then we have a main loop and we run and go, all right, we accept things, takes a file descriptor and an address to put something in, gets out a new client thingy. On the new client thing, we read until we are done reading, and every time we read the buffer is tiny to actually see that something happens possibly multiple times. It can be whatever size is suitable. And then we write, possibly in chunks, because neither read nor write on a socket guarantee you that they produce they send or consume as many bytes as you tell them. So you may need to chunk that up. So if I run that thing, it's great. I can just run it. Okay, a little bit of annoyance over here, and go and connect to it. And here's my hello server, and it says hello. But what it doesn't do is, if I run another instance of my client and I say, well, maybe I put the world thing over here, it doesn't say anything, which makes sense. There was nothing asynchronous in our code. It's fully blocking. So the second connection basically waits for the first one to finish, and this is, roughly speaking, the core of what I want to fix. So if I quit that guy, you see the world comes out, because now the first client unblocked, everything gets destroyed, and we do the other guy. So that's not, but this is not what we want. We want to have multiple clients. It is not very interesting. So we need to somehow make this whole thing asynchronous. And I will start off with the accept and build most of the infrastructure around the accept, and then do the read and write as well. So what we really want to do is over here, this accept, we don't really want to have it blocking. Well, if we don't want it if we do not want to have it blocking, we can start off and say, all right, let's co-await that thing. And I don't want to interfere with the real thing, so let's call that async accept, just so it has a different name. But I'm in main over here, and main is not a coroutine. Okay, fine. So I need a coroutine. Now, getting a coroutine is relatively easy. I had a task up there, so I create a task. And I just use a lambda over here. Lambdas can be coroutines, although they're a little bit weird. It's not really useful to have any lambda capture for coroutine, because that does not survive particularly long. So any context captured needs to either be in the body of the coroutine or in the parameters. So I will take care of that. This has nothing to do with any of the things I'm doing specifically over here. But we want to create a task, okay? And the task does whatever we have inside over here. Okay, great. Let's do that. Let's indent that a little bit so that we can see that a little bit clearer. And then I think this is a coroutine done, and we will call it. Now inside over here, it currently undersquiggly the async sync, because I haven't implemented it, and it undersquiggly the server. All right, well, the server we already have. Let's pass that through. So we have the server just as parameters, and we put it over here. The type of that is this little resource manager, so we stick that in. And then the server should be fine. So this is kind of making the async accept asynchronous, if we had it implemented. So let's implement it, just to show that there's nothing magical or complicated in creating an async accept. So we'll just copy the signature as a reminder what needs to be done, and create a struct which becomes my async accept sender. So the first thing this guy needs to declare is what kind of entities will that be producing on the set value calls. And it will just create another socket, so we put that into the same resource manager and declare that. The P2300 proposal doesn't use exactly that name. It uses a little bit more complicated thing. But over here, we'll do a simplified version, very similar to the concurrency stuff Eric Niebler showed on something like CPP Europe in a couple of months ago, which inspired me to say, all right, I can do the same thing he did for threading for networking. So we create the result, and this is, okay, I need to type it correctly. So we have a result type. We already know how we want to construct this thing. So there are basically a bunch of things in here. So there's a file descriptor. Okay, we need to capture that. There's a sock address pointer. This is the address, which just happens to be on the coroutine stack. But the coroutine stack actually goes into the coroutine frame, so that will actually nicely live. There's no problem with that. So let's say we have an address. And then because it doesn't know upfront what the length is, we also get a pointer to the length, So we capture that as well. So this is just so that we can do the construction thingy, and we're pretty much done with this guy. And then a sender has one primary operation. It's basically a friend, because it goes as a first argument, explicitly returning a state. It's called connect, taking an async accept object, okay? And this guy also takes a receiver, R. I will just call it R for now, and the type of the receiver we don't know. So we make it a template. Easy enough. And then all we need to do over here is to say we return something, and for now we just return that state. Oh, we don't have a state, fine. The state is just another class. So there's a little bit of fuffing about with classes, a little bit boilerplatey things, but users are normally not expected to actually write these guys. So the state has a function which is void. It doesn't return anything. In the real thing, it's also no accept. But I don't bother with all the annotations over here, just making it simple to keep the time at bay a little bit. So we basically get a start which gets a state reference, and for now we don't do anything. This should satisfy the sender interface. So if everything goes well, this should now already compile, and it didn't go well, so I did something wrong, probably something silly. What did I do wrong? Oh, okay. So what I did wrong is, over here is I created a T and I'm not using it. For now, I will punt on that and just ignore the T for a bit. Okay, so this is compiling. Now, this doesn't do anything. We want to do something. What do we want to do? Well, the idea is in the end to get asynchronously in one thread with networking. You actually just delegate the asynchronously to something like poll or epoll or KQ or IOU ring. I will use poll because it's the easiest and quickest to type. The real implementation would almost certainly use rather something like IOU ring or KQ or IO completion ports. All of these things work, it's fine. But basically what we want over here is at the point where this operation gets started, there's probably no client. So we basically want to register that we want to read on the file descriptor and want to get called back once we're done. So let's pretend we have some kind of context where we just add our operation. So we just add the file descriptor, we want the event we are interested is poll in, and we want to get back to ourselves. So that looks like a great start operation. Now but actually this is a friend, so we actually need to get these things in here, and we don't have a context. Okay, let's get a context. And we also don't have a file descriptor. So we actually need a bunch of things over here. Let's start with creating a context. I call it IO context. And all of these things will eventually end up in the state. So we basically need to build that up. The state will also, because the state is the guy who's completing things really, it will need a reference to or pointer or something, or an entity. It basically needs the receiver to complete. So let's put in a receiver over here as well. So we get a receiver. Okay. I will not fully indent all of these things because it's kind of boring. So now obviously I need to pass all of that stuff through. This guy gets a state with a receiver, and because I will need later to actually create a constructor, I'll just make it like so. So this guy, and we need to pass all that stuff through. Okay, that's a little bit annoying, but fine. So we have the first guy is the receiver. Then we have the self-context, self-file descriptor, self-address, okay. And a real implementation might actually put that into a tuple, but then it becomes a little bit, and then have that fairly generic. So we don't do that only once. But that makes the code a little bit less clear on what's going on, and I would like a little bit of clarity over here. So we just pass these things through. And now the key business missing is actually we don't have an I/O context. So what do we want from our I/O context? Well, relatively straightforward for now. We actually know that we have an add function, which gets a bunch of arguments. Let's punt a little bit on what they actually do. And I actually forgot, because before I get off over here, I need to give the parameters over here names. So this is self and this is receiver. I'm passing through these things over here by value, primarily to reduce typing and forwarding stuff. Real implementation would actually pass all of these things with appropriate references and possibly have two overloads for connect, or deducing this, one of these things, to deal with const and R-value references. So, but for a demo, this is basically just a toy implementation, right? A real implementation is more complicated, does more things, avoids some work, but conceptually it does the same thing. Okay, so we add the context, and I think we should be again in a state where things should mostly compile, except they don't. Oh, yes. So we didn't have I/O context, so let's create an I/O context. It's probably relatively a global thing, but we don't use it as a global variable, so we can have multiple of those, and we just need to pass it through everywhere, and to get the interface done. So let's put a context over here, and the async accept also got a context as a starting point. So. Okay, hopefully this is everything. Yes. Now, let's concentrate on what the context does. So this is the guy who actually deals with our asynchronicity. So we are just being given basically a file descriptor and it's actually a short events, which is basically indicating what we're interested in, and some kind of object we need to talk to. So I will call that just I/O to avoid a lot of typing. So I create an I/O, and I will just use type erase thing over here, so this guy gets a virtual function doing something like onReady or whatever you want to call that. Doesn't need any parameters. A real implementation may want to get the parameters to pass errors possibly through, but I'm not too keen on that at the moment. But this is just relatively straightforward meddlings. So if we get one of these guys, all we want to do is, well, let's go and say we stick them into something we can pass into Paul. So we have basically an array of Paul file descriptors, and because we want to have a continuation, we create a parallel array of I/O objects, I/O star. So let's call that operations. And this add, all it does is it puts these things in. So there's nothing super magically, it's just a little bit of typing, pushback of a poll FD, and we do FD is FD, and events is events, and our events is 0. Like this is. So when calling Paul, it will take the events as figuring out what it wants to return, and our events as the result, what actually happened. And then we want to have a parallel version of that for the operations. Everything fairly straightforward. I think. So now we have added these things. Everything should again compile, but nothing interesting happens. Okay, it doesn't compile. It doesn't quite compile because there's a little bit of an annoyance, and this is I need to actually derive this guy from our IO type. And now I have a virtual function in there, and structured initialization doesn't work, so I actually need to get a constructor, which is just a typing exercise. Right? We basically need to get a state where we get all of these guys in. Somewhere got my indentation wrong, but fine. So this is, if I were having an interview right now, I would tell the candidate, don't do that, I do that, why do you do the other stuff? Because I'm not interested in typing exercises, but over here it's not an interview, so I have to do it anyway. Context. Over here it would be nice if we had actually stuck all of these things into a tuple, then we could just move over the tuple and be done with it. Okay, so then we have all of these guys pushed over, and hopefully now it compiles. No, it doesn't. Oh, okay. So the other part is we actually derive from something with a virtual, an abstract class, abstract function. So we need to have our onReady function. We override that just to make sure that we actually match the thing. And for now, we don't do anything in there. Just checking that everything compiles. Okay, cool. We already know what we want to do though. Let's quickly do that. So the idea is we ask the Perl, is this file descriptor ready to read? And if so, it calls us. This we will need to still implement, but if we get called, we know there's a file descriptor we can accept. So let's do that. So we get a client, and we accept that guy from the file descriptor, and we pass in the address and the length. That's super straightforward. And, well, this may fail. So let's see whether that fails. If that is less than 0, then we basically set error on the receiver. So we basically go, all right, set error on the receiver we have over here. And what error we put in, and let's make it easy. We put in an make exception pointer. You can, in a real implementation, you can do whatever error codes are appropriate. It just needs to kind of compose. But for the simple implementation over here, the errors are just exceptions, just to keep things a little bit simpler. So we get an exception, we stick a system error in there, which we get from Erno, and then we need to tell it, all right, this is a system category. Okay, that hopefully was relatively free, and somewhere I screwed up a parenthesis. Oh, okay. There's too few parentheses over here. Okay, fine. Okay, so this is the unhappy case. The happy case is simpler, right? Because we just got a client, and we go and say, all right, we successfully did something, so we succeed on the receiver, and we want to create a file, this manager. In the real world, it would be kind of whatever stream socket created from the client. So we do that. So this is I think this is pretty much all we do in the accept sender. So there's nothing really complicated in there. There's a little bit of boilerplate. What is still missing is, all right, we have registered our interest in asynchronous operations, but we don't do anything with it. All right, let's do something with it. So give it a run function. And we want to do something if there's something to do. So we go, all right, while our file descriptors are not empty, we do things. Now, what we do is we go saying, well, let's pull, and we just go and this doesn't deal with poll errors. A real implementation would deal with poll errors, but it's not particularly interesting. So we both basically just go, we take the file descriptors, we get the pointer out of this data, we know how many there are, fds.slice, and we don't have a timeout for now. We could have a timeout, but not particularly interesting either. So if we have that, we need to move through our array of Perl file descriptors. So it's one of the reasons that Perl is not the best approach. It's simple, but it's not necessarily the best. So you may want to use something else so you get some of the inefficiencies out of there. But for simple implementation, it's entirely sufficient. So let's go over that, and I go from back to front, because when I'm done with something, I just remove it. And if I went the other way, that would be harder management. So let's not do that. Let's just go, we have an index, and we go from fds.size, and we decrement that guy, and then, all right. Now, in here, we look at all of these guys, and let's just deal with the happy case. So if at the point where we ask for events, we intersect with the events from our events, then there's something to do. Right? So we have successfully waited for an event, and it happened. In this case, what we want to do is we just want to complete. So we just want to call our onReady thingy, which basically kicks off the actual accept. Right? The Perl interface is a readiness interface saying, all right, this operation is ready to do. It isn't the completion. Other things like completion ports and IOU ring would actually tell about the completion. All right, once we have processed that, we don't need it anymore. So let's get rid of it. So we just erase it. This is also not super efficient, because I'm actually moving things. If there's a huge array, I move things all the time. You could swap things. It's just a little bit more typing. Not particularly interesting, though. So let's keep it simple. All right. Now we have our context. Cool. So we can run something. Let's go and say at the end, once we have set up everything, we just kick off our context. Unfortunately, it doesn't do anything yet. The reason it doesn't do anything yet, we have created our coroutine, which is a sender, but we haven't actually put the sender together with some kind of receiver to kick it off. So we need to do that as well. All right, let's do it. So I will put that corresponding kickoff also into the context. There's nothing particularly, it could be in some other entity, because it actually has nothing really to do with the context. But the context is an entity we already have around, so why not? So we don't need that anymore. And we have a context spawn. All right, let's implement context spawn. We know what context spawn wants to do. It basically, well, wherever we implement it, is, so we get, let's start off with what it gets. It gets a sender, and we want to spawn it. And it will look a little bit dodgy. I know that it will. Everybody will go, oh, this is a resource leak. Man, you have a resource leak over there. Get rid of the resource leak. Because I will just new a job which I will create with a sender. And I need to forward the sender. The coroutine thingy is not copyable. Most of the other things I have over here are copyable to keep things simple. But this guy is not copyable. So I create a job. The idea of the job is it will create the operation state and start the operation state and do all of that in the constructor. And the start function itself cannot throw. It's kind of one of the preconditions. Once it's started, we know that the completion is called. So we can actually use the completion to get rid of the job. And this is the entire plan. And then everybody using I/O context just gets that thing out of there. And we have basically one allocation for each client joining in. So again, we know what we want to do. So this will take a little bit of indirections before we actually get there, but that should be fine. So we have a sender and we get a job. And I will, just to make sure that that I get a forwarding reference, I can forward, make that a template as well, although it's just the same type. So this is where the sender goes. And in the sender, as I said, I really want to do something like a connect with my sender, okay, and some receiver which I don't have yet, right? So there's some things missing, and that produces a state. So let's give that a member variable state, and we will figure out the type. This is a little bit ugly type, but it's fine. And we need to forward that sender actually, because it needs to be, it's only move constructible. And the receiver we construct, we want to get rid of the job. So let's give the receiver, although it gets embedded into the entity, just a pointer back to the job. So we go and give it a pointer to this. Let's concentrate on the receiver side first. So we already know how the receiver kind of needs to look like. There's nothing magical in here. We know it has some, well, we just constructed it with something. Okay, I will call it job base because it's easier to deal with. So I will also have a quickly struct job base. Everything can be solved with another level of indirection. That's what happens over here. So we have basically a virtual job base, which doesn't do anything special. And then we get a job base. This guy now needs to become a job base as well. Fine. Job base, and I need to put a colon in the strategic point. And we get a job base. Okay, excellent. Now, all the receiver does is it basically gets called when there are completions. There's 3 completions. I will only implement 2 because I don't deal with cancellations for now. The first one is, let's say we get a successful result. So set value gets a receiver itself. This is ourself. It does get a result, but we actually don't know in this generic context over here what to do with the result. So we actually just accept it and throw it away. That may not be great, but most of these, like the task sender, actually creates a non-entity, or in a real implementation could just say, okay, it doesn't return anything, and you can just deal with it. Important is that we get called, and so that we can clean up. So we clean up our job. And the set error, for the error, it's probably more relevant to do something maybe, who knows, but for now we just get rid of the error as well. Okay, so now we have our receiver and we have our connect. Now the question becomes, what is the type of state? Well, we kind of know what it is, right? It's the return type of essentially this expression. So we just go and say, all right, yeah, great. Our type is a decal type of this expression, and we call that state. Unfortunately, we cannot write that expression. We cannot write that expression because we actually do not have a sender around. But we know the type. We know the type of a sender. We can conjure something up which is good enough to figure out the type. So we go a decal type, decal val of sender. And likewise, we don't have a this for the receiver, so we cannot construct one. So let's get a decal val of the receiver. Okay, nothing super complicated. And now we basically have created a state. If anything fails over here, the job gets cleaned up. So if there's an exception thrown in any of that, fine, nothing happens. And then we need to make sure that we actually kick this thing off. So we start the state. And that's pretty much our job. And if everything goes well and I didn't have too many typos, then it compiles and links, and it does. And we can actually, we are kind of back to a state where we have an asynchronous accept, but it will not do a lot, or it will not look any different than before, because when we go over here and we connect with one of these guys, okay, this guy works, this guy doesn't. And it doesn't because we haven't made the read for the first client asynchronous, so the second client still doesn't get a chance. Okay, so we need to deal with the other asynchronous operations. So we're gonna do that, which is actually also quite fairly straightforward. And in fact, all we need to do is over here go and say, oh, okay, we need an async. Well, let's go and call that co-wait async read sum. And the other one we call co-wait async write sum. Right? And then we need to just implement these things. But the idea of how to implement them is actually quite exactly what we did with accept. We capture the data, we signal that we are interested in readiness. Once readiness happens, we call the corresponding operation and we're done. There's one thing before actually going there. There are basically two different operations, right? Over here, the async accept And then once we have a new client, we have another kind of context. So we probably want to spawn our own client thingy over here. So we basically do something very similar. We get our client, and we stick that into another coroutine, just closing it out. And the coroutine, similar as the other one, gets a few parameters. There's the context, and we need to move in our description. In this case, we need to capture that because once we loop around, this guy goes away from the context of what we want to changes. So we want to capture it by value, which should basically complete what we need to do in the main function. And then all what's left is another little bit of typing exercise. So we basically need to go and say, all right, okay, we have an async accept. And we turn that accept effectively into, let's start with async read sum. And before I forget that doesn't return a file descriptor. It returns an integer. How many things did I read? And we actually read, and we actually get an n over here. We check whether n is an error. The error handling actually stays in this case exactly the same. This guy becomes n. God, if I could type. And we need to make sure that our connect is actually the one we are interested in, so the read sum one. And then we should probably, although this would, okay, it doesn't quite work. We probably should rename the address thingy over here. We don't get an address. We really get something kind of a block of data. So let's replace all of, oops, not this one. We want to replace all of that with data. No, not that one. Okay, there should be all of those, and then it's not a socket address, but instead we get a char buffer. So let's fix these types. And the sock.lang.c pointer is actually not that either. So we get a sock.lang thingy, and is actually an std size t would work, or could be an integer, whatever. Okay, now I think I have done all the modifications to actually implement read sum. And we can just do, and this is a better base than the accept for the write sum. So let's turn that into write sum. So we basically go here, write, not ready, write, and the thing which I always forget, I won't forget over here, we don't register interest in reading things, so we don't use pull in as an accept and read, but we do pull out. And so when the thing is ready for writing. Okay, if everything goes well, then, okay. Of course, nothing goes well ever. Okay, this is. And another little error. Invalid initialization of reference from OK. Oh, okay. So what I forgot to do is this guy also needs to put through the context, and likewise this guy. Just so that we know where our completions works. Okay. Okay, now things compile. Excellent. Let's go back to our test and go, right, now we should have actually a fully asynchronous thing. We can say, okay, it's a little bit, okay, let's shout hello over here, and we go to the other guy, and we can spawn up as many as we want, pretty much. This guy works as well. So basically, now the entire thing is nicely asynchronous. People say the resulting code is, roughly speaking, impossible to write and comprehend. The actual body of the, or the key work of the fully asynchronous echo server actually fits on one page. Right? All we added is we have a little bit of a creation of a coroutine and sticking this coroutine somewhere. Right? We do that twice because we have actually two different kinds of activities. One's the accept and one's the actual client operations. And then we put a little bit of a co-wait over here. We renamed that. We need to put in a context. In this version, I believe it's possible to actually inject the context into the awaitable, and a real implementation would not use a context, but a scheduler to basically inject the context. So you actually would get rid of that. It's a little bit more complicated, but it should be entirely doable. And likewise, over here we did put a co-wait, rename the function, put in a context, and we probably don't even want to do that, and we have a fully asynchronous thing. So this is pretty much what I wanted to present, and I'm entirely open to any questions on any of these things and how that works or where that goes and things like that.
Quick question about the style of your coding. Actually, I know that's not maybe what you were looking for questions for.
Okay, that's fine.
But the one little question about your class member initialization using the same names as your parameters.
Yep.
Is there an obscure rule that I'm missing where that's not ambiguous?
Yes, there's an obscure rule which says it's not ambiguous. This is basically what you're talking about. Is over here these guys. Yeah, you can just use the same name. It's fine. I think the rule along the lines is, all right, the member initializers are, or the members are named, but the arguments things are not in context. It's somehow it says explicitly, so that's perfectly fine code, and I think it's way easier rather than coming up with a different set of names. Although in many contexts, you would have a prefix or suffix or something like that, but it's just a little bit of a typing exercise over here.
I thought that I had done this by accident before and hit a bug myself, so it may have been a different situation.
Okay, it does not work if I were inside a function. Let's say I go over here into this function and I do something like, okay, this guy doesn't get an argument. Let's take a function which does take an argument.
Right, inside the body, the name is ambiguous then, right?
Yeah, well, it's not ambiguous, right? If I do something like fd equals fd, this is undefined behavior, there's no ambiguity. The second fd is actually a new declaration, and this is in scope for the initialization. So that does not work, and it also doesn't work if I put parentheses around that. So it doesn't matter.
In the body of a constructor, the name one would hide the other, probably,
yes.
Right? Yeah.
Yes, that's correct. Right, it does work in the member initializer list, though.
The other question is, what's the significance of using the friend member functions as opposed to normal members? Is that just a convenience?
Well, it's not much of a convenience. This is basically allowing the things like connect and start to be customization points, which you can find and override. And the overriding bit is important when you can detect in a real thing with sender algorithms and you see things being combined. You can then go and say, oh, this combination I know how to do differently or better. For example, put it on a GPU or something like that, and the general algorithm wouldn't work. And if you make it a member, you have no hook into customizing that. So this is the main significance of that. This implementation over here doesn't really try to do anything like that. The real implementation would actually have a connect, which is a customization point.
Thank you.
Okay, anything else? Otherwise, I'm quite happy because I must be either super clear or nobody understood anything what I'm doing at all. I hope for the first. But
the job as a template parameter on the class, which is sender, and then the constructor also as a parameter, which is a template in the sender.
Yes.
And the state type, one is created with the connect to the decl value of the sender, one with the S.
Yes.
So doesn't that require that S and sender is the same, or at least result in the same state? Like why that indirection?
Oh, well, okay. So I think it's more common for people to see the forwarding with a forwarding reference. So I wanted to make it a forwarding reference. It would actually work because I don't faff around with the sender and forward it directly over here to write sender direct. And it doesn't matter in this case. They are the same type. In a real implementation, they may not be the same type, and because there's something like an remove CVRef around that, and then the forwarding reference deals with the actual forwarding, and the sender with the CVRef around that deals with what is actually being called in the end. So in this case, it doesn't matter, right? It compiles just fine and does, or doesn't. In constructor, S, yeah. It does not compile because I don't have an S anymore in my constructor in the job. So I need to change that to sender as well. But this is, yeah. In this case, it doesn't matter. But it's just, it remains a forwarding reference it got from the actual call and spawn, right? You can see that over here it's a forwarding reference, and I actually pass in the type and forward the thing to have the same type. So actually, they're the same type. It doesn't matter. Okay. Anything else?
Oh,
yes. Oh, yes. Yeah. Good.
Could you show the? Sorry. Could you show the connect and start again, and maybe run us through that real quickly, because that went a bit fast for me.
Okay. So I guess you talk about the job connect over here, yes. Right? So to actually kick something off, I take a sender and a receiver, and I connect them, right? This is this expression. And what I get out is a state. And the state is actually not movable, so the only way for me to capture that is I directly initialize it into a state object. Right, I get that. Now, there's a little bit of huffing about, kind of I need to replicate, roughly speaking, the same expression to pull out the type. And Francesco's comment was, well, the types are not really quite the same, except that they are, and it doesn't really matter in this case. So we figure out the type, and well, then we have a state, and on state objects we can start. This is all which is happening over there. And the nice business over here is there's no chance for me to drop that the job allocation which I did at a different place with new is dropped on the floor, because the connect can throw. That's fine. The constructor hasn't started running, so the entire thing would be cleaned up automatically by the runtime system. Actually, even if the starts through. And then, so safely to clean up. But the promise is, once I start something, one of the completion things completes. This is the key reason. And then I need to make sure, which is happening over here, that all completion signals clean up the job. Did that clarify?
Yes, thanks.
Okay, cool.
Comment from online. If I remember correctly, the CP is tag invoke, connect T, etc., but I didn't see tag invoke.
Okay, so if I understand the question correctly, I'm not using tag invoke over here to simplify things. The P2300 uses tag invoke for all of these things. So I would actually not write something like start. I could actually show, if you're interested in how real implementation would do that. Let's go with a simple version of start. It would still be a friend, but it would be tag invoke. And the idea of tag invoke is you have basically one name which is taken, tag invoke. Nobody can take tag invoke for anything else, but the name start is not taken, because instead of passing that as a name, we pass it as a type. We would have something like whatever. Stood execution maybe, colon start T, and then still get our state. And by doing this, you basically can namespace names you can customize. This is the entire tag invoke discussion, how to do that. It is also kind of quite nice, because if I had that, I could actually, in the receiver I had, both of the receiver operations set error and set value do the same thing. I could actually use tag invoke and have the first parameter type be a template, so I can actually deal directly with all the signals using the same code. So this is a tag invoke business. I haven't used tag invoke over here just to simplify things. I also haven't used this cancellation, also again to simplify things. It would probably take about an hour or something like that to fiddle the cancellation in there. None of these things are per se complicated, and I wanted to basically get across the idea of how things work. Okay?
I have a comment from Philip Gelman. Dietmar, you were super clear, and the live coding is very impressive. Thank you.
Okay, thank you very much for that. All right. If I was that clear, then thank you very much, everybody. And oh, wait. There's a little bit more. First off, thank you. And we are hiring. And there are pointers to the resources. The code is currently on a company laptop, and I cannot easily put it on GitHub. I will make very similar code available on GitHub over the weekend. Right, thank you very much.